to Steve Ripka.
Thank you very much, Michaela. And hi, everybody. My name is Steve Ripka. We're going to be doing a presentation today on low delta T and correcting low delta T in buildings that are on district cooling loops. So some of this may be a review for some of you folks, but others, this may be some new information for. What we'll go over here today is what low delta T syndrome is, essentially the definition of low delta T syndrome, coil design and performance, and how these two things are related. So how my coil performs if I get below my minimum delta T. Why we want to maintain that delta T at the point of water to air to heat transfer. So at our air handlers, at our fan coils, and any of the devices that provide heating and cooling within our buildings that use hot or chilled water from a central energy plant. I'll talk a little bit about the more common building connections for facilities that are located on district chilled water loops. We're going to talk about direct connected buildings as well as decoupled buildings. I'll go into some of the causes of low delta T syndrome, how we wind up here, what has happened over years to cause the building to go into a low delta T mode. Low delta T and pump affinity, so how that decrease in differential temperature affects our pumping and how we can actually pump less water if we maintain our design temperature differential. Low delta T in the Belimo energy valve. So Belimo does have a solution specifically directed at correcting low delta T. So I'll go into a little bit about the energy valve itself. And then finally, I'll just briefly talk about a building in Nashville, Tennessee, where we corrected delta T on a facility that had its chilled water provided from a local central energy plant where there was billing based on GPM, temperature differential, and things like that. So what is low delta T syndrome? Essentially, to calculate BTUs, we use the formula 500 times GPM times delta T, and that will give us our capacity or our BTU yield of the coil. Low delta T syndrome would be the result of the inefficient use of chilled water at the point of consumption. So where the air passes across the coil, if we're entering our water to the coil, say at 42 degrees, and it is designed for a 12-degree delta, and if we start to return that water below 54 degrees, we get into a condition called low delta T syndrome. And here we can see how coils are designed. If we look at this very basic submittal example here, you can see that there is an entering and leaving water design temperature for this particular coil, a maximum GPM, and a capacity. So by running that formula 500 times the GPM times the delta T, we will get our BTU per hour, or essentially our capacity of the coil itself. In district cooling, it is important to maintain your design delta T, partly because utility rates can increase based on your temperature differential. So if your building has a contract delta T of 14, and you start to return the water at or below 14 degrees differential, you can actually incur penalties, or what people call fuel inefficiency surcharges in some cases. And the lower the delta T, the higher that penalty can be. Utility rates also increase during demand hours. So if it's at a high demand load, you want to be using your water as efficiently as possible to not incur additional pumping through the building. So making sure that we're using as much of the capacity of that water at the point of water to air heat transfer to keep the pumping as low as possible will actually keep our overall energy bill down. If this problem is addressed at the plant as opposed to the building, so if the local utility provider simply starts to decrease the amount of water being pumped from the central energy plant or the utility plant, then the problem can be shifted actually from the central energy plant to the buildings. Of course, we want our cooling coils to never operate below their design delta T. When we are at max flow, we want to be at our design delta. If we are at minimal flow or lower flows, we actually want to be above our design delta. And finally, supply water temp shouldn't be increased to a point that we compromise coil performance, air conditioning, and of course, especially dehumidification. So I'm going to talk just a little bit here about the different district cooling building connections. The first group is going to be the direct connected buildings. So here we have a very simple example of a direct connected building with a booster pump. And simply, the booster pump adds head pressure to guarantee flow. But it could also compromise flow to other buildings on the loop. We have a pressure regulating valve that actually reduces the supply side pressure to the coils and the valves. So let's say if this building is closer to the pumping station or closer to a central energy plant, it may see higher pressures than other buildings, and this pressure reducing or pressure knockdown valve can be installed on the supply side to limit the pressure through the building and, of course, to help maintain optimal minimal differential pressure. We have a direct connected building. This is about as simple as it gets. We just simply have an entering chilled water pipe and a return chilled water pipe, and the building is really reliant on the pressure provided by the central energy plant or the distribution system. So at high load conditions, you may see more flow and compromised differential temperature, and at low load conditions, you may see lower flow and possibly have the inability to actually meet the load demand in your spaces. We also can find conditions where we have directly connected buildings with a booster pump and a bypass. This is a fairly effective system. You have a bypass line that goes around your booster pump, and in low load conditions, you simply run off the system pressure. As your demand increases or as your load increases in the space, the pump can be ramped up to increase the pressure and provide cooling at higher loads. Then we come to the decoupled buildings. Here what we're looking at is a decoupled building with an entering water and a crossover control valve. So we can regulate flow with the entering water valve, and we regulate temperature in the crossover valve to make sure that we don't send water back at or above or below our design delta T contracted number. This can be a little problematic because as you take water from your return side and move it to the supply side, you start to blend water. So you start to blend moderately temperatured water with your entering 42-degree water. And again, this could have some negative impact on air conditioning and dehumidification. Here what we're looking at is an example of a decoupled building with a return water temperature control valve. And we simply recirculate the water until it's at design return water temperature, and then we let the water exit the building. So this is a very, very simple setup as well. And finally, a decoupled building with a heat exchanger. So, of course, the heat exchanger is going to completely separate the building from the distribution loop. We could have a little heat transfer loss because of the heat exchanger. However, this is a very effective methodology, especially when you're dealing with high-rise buildings and you want to decouple your building at a certain height so you don't have a high-pressure system. You can actually wind up with two medium or two low-pressure systems by installing a heat exchanger. So not an uncommon process, but of course the cost and the installation of the heat exchanger has to be taken into consideration at the design point in time when the building's being set up. District cooling and delta T correction also have a play on pump affinity. And we can see here I have two very basic examples. In calculating our delta T or our GPM, we use the formula tons times 24 divided by the differential temperature. So here on the top, if we see we've got a 100-ton system running at a 10-degree differential temperature, to get our required load or our required BTU yield, we need 240 gallons per minute. The formula below shows the same example of the 100-ton system, but running at a 12-degree delta T, or let's say even our design delta T, where we only utilize 200 gallons per minute. Now this 40 GPM differential doesn't seem like a lot, but when you take pump affinity into consideration, it's going to take about 73% more pumping horsepower to get that additional 40 gallons per minute based on that 2-degree decrease in delta T. So not only can we wind up in a situation where we are paying a penalty based on the lower temperature of the return water, but we also incur more pumping costs. So maintaining proper delta T does one of two things. One, it eliminates your fuel inefficiency surcharges or your low delta T penalties. And two, it ensures that you're pumping as efficiently as possible through your system. Lots of causes of low delta T. Some buildings have different equipment that was designed for different delta T's, stuff's been added, stuff's been removed. Three-way valves, of course, bypass water at partial load. So we start sending our design supply water temperature back to the return and not pushing it through a heat transfer device. So that can be very wasteful. Resetting your supply air temperature above set point can lead to unstable control, lower return water temperatures, and also compromise comfort in the spaces. Coil piping has to be done correctly. It's amazing how you do find coils that are not piped with water flow, counterflow to the airflow in facilities, and this does compromise return water temperature. Of course, the bypass and the decoupler, necessary evils in our system, but they do send supply water back to the return side and compromise that overall return water temperature. Very common problem that causes low delta T is oversizing. Happens at the equipment level, it happens at the point of generation of the chilled water, it happens at the valve level. People tend to oversize for safety. Controlling the chilled water valve just looking at the air sensor can be inefficient. So although we always need to run a discharge air routine, a space air routine, things of that nature, let's take the opportunity to look at the media creating the temperature change in the air. So let's look at our water. Let's make sure the water is being used efficiently and we're getting the proper BTU yield out of our heat transfer device, and we are also maintaining our contracted or our design return water temperature sensor set point. Manual balancing simply addresses the full flow condition and doesn't address part load, where systems frequently run at part load and not at full load. And then things get changed and people don't always rebalance their system. You know, with a pressure independent style valve, if you make some changes to your mechanical system in your building, the building will stay balanced. As changes happen, if people don't rebalance, the system winds up being off balance, not only at full, but also at partial load. Another common cause of low delta T is laminar flow. So laminar flow is going to occur when water starts to flow in parallel layers. It doesn't mix. It's not turbulent. It doesn't clash against the walls of the tubing and the coil, and it does not give us our optimal heat transfer. Hydronic coils really are designed for turbulent flow, and if we get to velocities at or about 1 feet per second or lower, we tend to get this laminar flow condition where, again, the molecules line up and the cold water molecules in the middle of the pipe don't have the opportunity to clash against the wall of the pipe to create good heat transfer. What we've done at Belimo, and this is something we've done for quite some time now, is we developed something called the Belimo energy valve. And it's a handful of different components put together to make one off-the-shelf product, if you will. It's a valve with a flow meter, entering and leaving water temperature, and a smart actuator. So what we can do is we can actually measure flow, calculate delta T, calculate BTUs, and make sure that our hydronic coils or our air handlers, our fan coils, whatever the piece of equipment we're working with is functioning as efficiently as possible, but more importantly, functioning based on design. The engineers who design these air handlers and these heat transfer devices have very specific parameters in mind, and they are best to be kept in accordance. Let's make sure our equipment works as it's designed. No different than any other mechanical device. You want it to run as efficiently as it possibly can. So again, what we do is we combine a flow meter, entering and leaving water temperature sensors, and some smarts in our actuator. So Belimo's been known over the years to make some pretty smart actuators, and we've leveraged that technology to build this thing called the energy valve. And what we can do, again, is measure those flows, measure that temperature, and if we get off our design set point, our contracted set point, or whatever the set point that has been entered into the valve based on the system parameters, the energy valve has a feature called the Delta T Manager. And what it will do, it will look at the request from the DVC system, the measured flow and temperature values, and it will correct the flow to reestablish the delta T to get it up to set point. so that we don't have compromised differential temperature across our air handler or our other coils. So some years ago, we did a little installation at a building in Tennessee. It was a very basic building, a stacked commercial office building, 15 stories with 15 air handlers. The flows ranged anywhere from 71, 72 gallons per minute up to about 86.5 gallons per minute. Based on the information from the building meter, we were seeing an average delta T somewhere between 8 degrees and 11 degrees Fahrenheit. The facility was paying an average monthly low delta T penalty of a little over $1,000, and our maximum average flow through this facility was in excess of 550 gallons per minute. So what did we do? We did something relatively simple. We installed 15 energy valves in this facility with an overall cost implementation of $53,474. By correcting the low delta T at the point of water-to-air heat transfer and reducing the pumping, we were able to create an annual cost avoidance of a little under $23,000 a year, return on investment of about 40%, a simple payback of 2.4 years, and we reduced that minimum and maximum average GPM by a little over 200 gallons per minute. So not only were the low delta T penalties reduced, but the actual pumping energy used to operate the building was reduced greatly. So that's all I have today on district cooling and low delta T. I'm certainly happy to open things up to some questions. Thank you.
Thank you so much, Steve. As a friendly reminder, if you'd like to ask some questions, all you need to do is open the question box, type in your question, and I will read them aloud, and Steve will answer them. Also, don't forget, we do have a handout for you today, and you can simply click on the handout box and download the handout accordingly. Okay, Steve, I have a couple of questions for you. Are you ready?
Sure am.
Okay, first one. Does the delta T manager take into account both delta T of water and the air to optimize both pump and fan energy?
It does not look at the air side. So the delta T manager strictly looks at the water side, and the controller running the air handler would have to work in coordination with it to optimize the air side on the fan.
Okay. Oh, sorry, a bunch of questions just came through. What is the best location for installing energy valves?
Generally, we like to see them on the return side of a coil. So say the return side of an air handler, a fan coil, things like that. They are applicable for supply side piping as well. And then there are some other off-standard or non-standard applications we can look at. If we can get an email address from that person, I'd be happy to go into that in a little more detail offline, Michaela.
Okay, perfect. Okay, next question. What would be the best application for the energy valve from Belimo? AHU units only?
That is where the bulk of the intention was emphasized. Yes, air handler units, they're the bigger consumers of chilled water, so they're going to be the units that can be optimized the most, and yeah, air handlers are really the primary suspect, if you will.
Okay, next question. Are there any plans to make the energy in a NEMA 4 version, not just the weather shield?
At the time, I do not know the answer to that, Michaela. That's something I would have to get from our project management team, but I can certainly look into that and, again, respond to that customer directly.
Perfect. How would this work on an old coil where none of the coil information was no longer available?
That's a great question. One of the things I did not go into during the presentation is the energy valve has the capability to data log. So it data logs a bunch of information over two different specific data sets, a short-term data set and a long-term data set. So what we could do is essentially size the valve as best or as accurately as possible, put it on the coil or the air handler, and monitor it and just see how it performs. Then the data can be extrapolated from the valve And we have a tool that has been built called the Energy Valve Data Analysis Tool. That information can be pushed up into the data analysis tool. We can actually analyze the performance of the coil and then set the flow and temperature parameters based on the information we have found. So it takes a little bit of time to get that first data set, but once we get the first data set, we can make some very educated decisions on how to operate that coil as efficiently as possible.
Next question, what is the smallest energy valve available? My application is a small 1 to 3 ton fan coil with flows ranging from 1.5 to 5 GPM.
We have a half-inch valve that I believe the low-end flow setting is 1.65 gallons per minute. So we can accommodate those smaller flows for certain.
Okay. Does the energy valve override the control signal from the building management system?
To say it fully overrides it, it repositions the valve. So it's always reading that signal from the control system, but it will reposition it to a degree to slow the water flow down and raise the differential temperature. However, it does know that you have a specific request coming from that system, and it doesn't completely just close the valve arbitrarily. It keeps all the factors in mind while it's repositioning to make the coil as efficient as possible and raise the delta T without compromising temperature.
What feedback is received from the water temperature sensor?
The water temperature sensor is a PT1000, so it's a standard resistive type sensor, and that simply just feeds back into a terminal strip on our housing, and then it's either displayed in the WebView web server or can be exported out via BACnet objects or Modbus registers.
Okay. Next question, can you speak to the energy benefits of correcting low delta T and in a multiple chiller plant, running fewer chillers? Do you have any case studies you can reference showing cost and performance benefits for such a scenario?
Yes, we do. We have multiple case studies that we can send the customer, and we also have a tool that can be used to sort of estimate potential savings based on the correction of low delta T. And again, Mikhail, that's another situation where if you would like to get the customer's email address, absolutely, I can send them those things and also reach out and discuss the savings estimate.
Of course. Was the Tennessee project running in the Delta T manager mode?
Not at first. So what we actually did, we had a situation where the design of the valve didn't meet the exact design intent of the coils. So we put 3 valves in just a test mode where they ran in basic pressure independent mode for a few months. And then we went through that process I mentioned a little earlier where we went to the site, we pulled some information out, and we made some calculated decisions based on the information in the energy valve. I will tell you that just by correcting the temperature and the flow on those 3 units, we did see an incremental increase in the overall building delta. And then when we went back and installed the remaining 12 valves, we already had a pretty good baseline to work with, so we knew where we could optimize and where we couldn't optimize. So the second round of installation, which finished off the building, really was very smooth because we had some historic information based on the first 3 that we had installed.
Okay. Getting a lot of questions, so I'm just going through them. Okay, the valve lowers the flow to increase the delta T. Is there a min flow set point in the flow?
Okay, there's a couple things. So what there is a minimum delta T threshold. So there's a set point you can enter in the valve and say, at or below 30%, 10%, 20%, whatever that number that you select is, the delta T manager will not engage. So that's one feature we have. We also have a second feature that we call VMIN. And what that is that's just a minimal flow set point at no command from the DDC system. So at 2 or 0 volts DC, the valve can maintain a minimum flow. I hope I answered that question as correctly as possible.
Does the Belimo does the Belimo energy valve go away from using CV sizing? Is it more based on GPM?
It's totally based on GPM.
Do you need a certain number of pipe diameters upstream and downstream of the valve to get an accurate reading of water flow similar to a standalone flow meter?
With the Belimo metering technology, you need 5 times the diameter upstream or before the flow meter in the valve assembly, but there are no downstream requirements.
Is a connection to the cloud required to use the energy valve?
No, absolutely not. The energy valve can be ran on a standard 3-wire control circuit that includes 24 volts power and a modulating 2 or 0 to 10 output.
Can the energy valve be used with secondary pumps serving each large air handler system with secondary pumps running on variable speed drives? How does the energy valve control function with a primary secondary pumping system?
It works very well with primary secondary pumping systems. So if you have a standard primary secondary loop, it works very well in those cases. If in fact you have secondary or tertiary pumps dedicated to a specific air handler, you may actually be able to achieve the delta T management simply by varying that pump speed. So it may be a redundant installation.
Okay. How does the energy valve differentiate a maintenance problem like a dirty coil or filter from poor automation control?
You're going to see lower delta T's, and those lower temperature differentials are just going to have to be viewed as a red flag, and someone's going to have to go take a look. So to say we don't take a dirty filter switch input or we don't take an air side coil fouling input, we just would make that assessment or make that observation based on our temperature and our inefficiencies in control across the air handler itself.
Could the energy valve potentially be used to help low delta T syndrome on a process cooling system for integration with process loads if the process controls allowed? Any experience with this?
A little bit, and yes, it just has to be looked at on a case-by-case basis. But I do have a couple instances where we have done some process cooling, and it's worked pretty efficiently. And now we do have Modbus capabilities in the energy valve. Generally, most process facilities are ran with PLCs that speak Modbus communications. So we do have a little more flexibility today than we have had in previous years.
I'm going to take a few more questions. Unfortunately, I have a lot of questions in the question box that we are not going to get to today, but I can reassure you that myself and Steve will reach out to you to assist you in any questions that you have brought up that were not answered. So the next question, the last questions I'm going to present to you, Steve, are, have you had any issues with valve causing issue with the PID loop in the control system?
No, we really have not. I have not come across that. Generally, if your PID loop is tuned for a standard pressure-independent valve, it works well with the energy valve.
Okay, last and final question. Can we use the energy valve to optimize delta T to a water-to-water heat exchanger?
Yes, you can. Yes, you can. And there's a couple of ways of going about doing that. Again, I could probably go into a little more detail with that customer directly offline.
Perfect. Well, once again, thank you so much, Steve, for your presentation. Thank you to everyone who participated in today's webinar. We got a lot of great questions and insights from everyone who participated. We look forward to having you participate in our future webinars. We have one coming up in September, the 20th of September, and it's going to be on our zip economizer. I'd like to thank you once again, and if you have any additional questions, please feel free to reach out to Steve or myself. Thank you very much and have a great day.